Alright, so I'm going to talk about smart contracts and a new transaction version for that. But a project called New Transaction Version for Smart Contracts is kinda long. And apparently Bitcoin Cash projects should be named after weather phenomena like avalanche and storm. And Nimbus clouds make it rain, and we kinda want to make it rain transactions on Bitcoin Cash. So I guess Nimbus would be a good name. So I'll present you Nimbus today, a new transaction version for unleashing Bitcoin Cash's untapped smart contract potential. Alright, so we kinda solved scaling on Bitcoin Cash. That means the road how we'll be able to handle gazillion of transactions is clear. We already got canonical transaction ordering, graphene/X thinner kind of working. We got MERKLIZED trees and sharding under development. Now the transactions may come, but where are they? So I had a look. Yeah, all the exciting stuff is happening on Ethereum. Ethereum has 700,000 transactions per day, and 300,000 of those are for contracts. They pay a total fee of 37,000 US dollars per day, and recently even way more because of Tether. So I've actually gone through a freakload of Ethereum transactions, Ethereum contracts. But before like this whole Tether congestion. So the ones I was interested in were simple smart contracts. So stuff that could easily be done on Bitcoin Cash. And that means those contracts aren't too complicated, but like they aren't just token transfers and ICOs and Tether. So I found that for 24% of them, 24% of the transaction fees, Bitcoin Cash would actually be a way better fit than Ethereum overall. At least it would be if Bitcoin Cash could do simple smart contracts really well. At least it would be if Bitcoin Cash could do simple smart contracts really well. So in the areas where Bitcoin Cash could shine, there are gamblings, games, exchanges, and oracles. But of course, Bitcoin Cash isn't capable of such smart contracts at the moment. So as I've said, I've worked on a few changes to Bitcoin Cash protocol, and I've given it the fabulous name Nimbus, which enables sophisticated smart contracts on Bitcoin Cash. And for this presentation, I am proposing a project for this protocol change. Some of the proposed features are already on the Bitcoin Cash roadmap, and some will be really controversial, but I think it's better to shoot for the moon and miss than to aim for the mud and hit. Alright, some more on games and gambling. So there are kind of two kinds of games on Ethereum. So those with a high purchase amount and those with low purchase amount. For example, a game with a high purchase amount is Gods Unchained. It has only around $2 purchase amount minimum, and the reason it isn't lower is because of the transaction fees. But there are games with transaction volumes below $2. The games aren't really economical, but they're hobby projects, so kind of hobby projects. And we can see that the demand for these games is really high. For example, Clover.network, which just launched like 3 weeks ago, is already going through the roof with 30,000 transactions per day. And with Nimbus, the new transaction version, these games would actually become profitable. Because fees would drop below 1 cent, and additionally already profitable games would be able to lower their costs. And for gambling, the pattern is the same as with games. Gambling would also benefit the same way from Nimbus. So for exchanges and oracles, there's also great potential for smart contracts. Here are some frequently used trade volumes. Users have to pay two fees actually: the platform fees and the Ethereum transaction fees. And as we can see, for users, it's not too high of a fee compared to so Ethereum fee doesn't make it too much of a dent. But for the platform operators, the increase in revenue would be a dramatic increase. And yeah, especially for small trade volumes. So another area would be oracles. There currently is only Chainlink on Ethereum that's doing oracles, and it's actually that updating the oracle costs more than $4, and more than half of that is Ethereum fees. So if Oracle operators would be able to keep the transaction fee, their revenue would double. All right. So, but what are the problems that hinder contracts on Bitcoin Cash? Currently, we're having three main problems for making smart contracts become mainstream on Bitcoin Cash. The first one is redundant repetition. So when we call contracts over and over again, we don't want to repeat the whole contract in every transaction. Only the part we're interested in should be in the transaction. The second one is script. Writing scripts by hand might be fun for the first few contracts, but after a while it requires psychiatric treatment, I guess, which isn't too cool if we want to get new developers on board. And the third one is unverifiable tokens. It's currently not feasible for a contract to check if a token is a counterfeit token. So that's why I present Nimbus, a new transaction version that solves all of these problems and more. How can it do this? So let's tackle problem number one, redundant repetition. Bitcoin Cash already allows building simple, decentralized, autonomous organizations. How can this be done? We already know that we can make covenants using OP checksig and OP checkdatasig, combining them, which allows us to make repeating contracts, like Karol Tchaikovsky already made some of those. And yeah, those contracts always have to be kept alive when they're being spent. And when we add some clever logic to that, we get something like a DAO. And we are already doing this in SRP DEX. So a DAO is only useful if it can do different decisions, for example, spending funds, holding elections, auctioning off collateral, and so forth. In Ethereum, this is called functions. In CashScript, it's also called functions. But how can we allow different decisions in a contract? Currently, our options kind of suck. We have to add a big nested stack of OP if, OP else if, and OP end if. OP if, OP else, OP end if. And for a contract that's only called once, this isn't a big problem. But our DAO has to make many decisions over and over again, and it would be really wasteful to have a huge tree of all possible decisions in each of them. So, especially if the number of different decisions is in the hundreds, then that would be kind of a problem. So how can we do this better? The solution is Merkleized script trees. They're also called Merkleized abstract syntax trees, or short MASTs. It's pretty well known, actually. How do they work? They are a Merkle tree of different scripts. So say we have many scripts. We can build a tree of those scripts and encode it in a single hash, the Merkle root. And then users would send Bitcoin Cash to the Merkle root. And when spending the coin, the path to the script has to be provided. This allows us to have very large trees while still being compact, and only the path from the root to the script has to be provided, which scales logarithmically. This means it's very efficient for large trees and we can put all the decisions of a DAO in these Merkle roots and call them compactly, over and over again. So, next problem number 2, outdated scripts. This is kind of a big one. Scripts, it's really hard to work with. I actually read a message recently from Jonathan Silberblatt expressing this frustration. He wrote, "Where does this 520 limit come from?" Referring to the 520 push limit. And also from my own experience, it's really frustrating to use Bitcoin scripts. And let's be honest, nobody in their right mind would use scripts outside of Bitcoin. And as emergent reasons, and I talked about on the conference, it's kind of stupid. Ethereum, which is meant to be way more complex than Bitcoin Cash, but there's still lawyers and whatnot writing smart contracts like they're Vitalik. So, and to write some stupid contract on Bitcoin Cash, you have to be some mad scientist. So yeah, we should have a scripting language that's attractive to developers, not something that makes them run away. But what are the main problems with Bitcoin scripts? I see 4 main problems. The first one is outdated stack operations. Modern stack-based VMs use a very different model than script does. It makes it really hard to optimize, even by hand. And we can't use modern tools developed for JVM, EVM, and WebAssembly. They have local variables, a memory, and only a few stack operations. Which means writing a good compiler for a script is really hard. All that research that went into LLVM for optimization is basically for the trash when it comes to Bitcoin scripts. So, the second issue is scripts' embarrassingly limited arithmetic. It's currently not even possible to do multiplication. 64-bit operations aren't available, even though Bitcoin Cash amounts, the amounts in the transaction, are 64-bit. These operations are really absolutely essential to do finance applications. So, the third issue is wasteful loops. There isn't really a way to do loops in scripts. The only way is unrolling them into a long list of statements. This makes things such as voting with a variable number of participants impossible. Like if you had a DAO and have to count the votes of some election, then you need to loop over the votes and add them up. Yeah, and this is currently not possible. So, the fourth issue is the lack of proper transaction insights. There is a workaround, as we've seen, using object-sig and object-data-sig on the pre-image, but this actually wastes too expensive signature checks when none are needed. Transaction insight should be built in and not require some stupid workarounds. How can we solve those problems? So, transaction insight can be solved by adding additional opcodes, but the other issues are much more fundamental. They require overhauling large parts of scripts. So, instead of reinventing the wheel, let's have a look at already existing solutions. Yeah, we need something that has modern stack operations, powerful arithmetic, and efficient loops. What satisfies these criteria? There are many existing solutions for this problem, but none of them are as fast and safe as WebAssembly. If you know what WebAssembly is, you're probably thinking, holy Alan, what did this guy smoke and where can I get some? First, WebAssembly is like Turing complete, but hear me out. There's actually a lot of reasons to go this route. So, WebAssembly is fast, compact, safe, and it's deterministic. Second of all, Ethereum 2.0 will use it. They call it EWASM. there'd be lots of opportunities to collaborate. So we would create our own dialects. I suggest we call it cache assembly. It would actually be a perfect fit. The main issue is that WebAssembly is Turing complete, and that's bad. We don't want to get stuck in an infinite loop when verifying a transaction. But luckily this is easy to solve. But I will explain how later. First, let's look at what WebAssembly brings us. So, first of all, it means we can translate script to WebAssembly, which can then be compiled to machine code. We likely won't use this initially because it's at least 10 times more expensive to compile a contract than it is to just run it in an interpreter. So this makes only sense for big scripts that are called very frequently. But then scripts would be executed blazingly fast. This could be useful for adding new cryptographic primitives such as CK snarks or this new Halo thing without having to change the consensus all the time. But the real benefit comes when we're inverting the error. We can convert WebAssembly to script. This is where the real magic lies. It means that we can take a contract written in a higher level language, imagine cache scripts but amped up, and then we can use powerful tools like LLVM to compile that to WebAssembly. LLVM has a WebAssembly backend, which we then convert to script. This means we can utilize existing optimization and debugging tools. This would make it much safer, easier and convenient for developers, while also increasing the performance of contracts. This means we would be able to attract much more developers working on smart contracts. So, back to our previous problem, which we haven't addressed yet. How do we solve the Turing completeness? So, a script could contain many loops, which might run indefinitely. So, we don't know how long they run. And they might run forever. But we can solve this by exploiting a central property of Bitcoin transactions. They are stateless. So when verifying a script, it will always execute exactly the same calculations, no matter what. So this means we can simply run our program and count how often each loop executed. We will know, okay, this loop ran 2 times and that loop ran 12 times. And when we want to spend the transaction output, then we put this information into the transaction. So it becomes a part of the transaction. And then when a node wants to verify the script, it can easily reconstruct the computation. It simply combines the code and the loop counts, which will be known to terminate. And then it will know exactly how many operations it will run before running them. This means it can make a precise calculation of how expensive a transaction will be to verify before verifying it, unlike Ethereum. So we do know how expensive it will be to run the script before even running the script. And then a transaction simply rejects then a node simply rejects a transaction it deems too costly to verify, and it doesn't even have to run it if it's too costly. So that's good. On to our next problem, unverifiable tokens. So what do I mean with that? Oh, here's a contract, and it wants to take a token as input. For example, 4 USDH. But anyone can make a transaction that appears to send any amount of any token. How can the script know if the token is a counterfeit? How can it know if it's fake? We could do a complete DAG check for all ancestors, but that's way too expensive and out of the question. In the past we had proposals to add OP group, but that was a bad solution, setting a bad precedent. So what can we do? Let's have a closer look at this transaction. It has two inputs, one with 3 USDH and one with 1 USDH. Now my solution Nimbus allows adding a little script into each transaction. I call this the preamble. When the preamble fails, the transaction will be invalid. So, we can make the preamble verify if the transaction follows the SLP rules. So the script would check if the sum of all inputs is greater or equal than the sum of all outputs. Clearly this isn't enough, though. The input transactions could be fake too. And the input transactions of those could also be fake. Can we prove that all previous transactions are valid? Yes. We can use a proof by induction. When we know the base case is true and we know each step is true, then the whole thing is true. We can use this by checking if all input transactions contain the SLP verify script. The SLP verify script looks at all inputs and checks whether all inputs have the SLP verify script as preamble. This won't work though yet. We cannot create such a transaction without having one first. So we need to have a genesis transaction that starts the whole chain. So the SLP verify script will have 3 rules. First, it will verify outputs don't exceed the inputs. Second, it will verify that all inputs have the SLP verify script as preamble. And third, an input is also valid if it is the genesis transaction. How can we use this in a contract? So let's go back to our contract in the beginning. It requires 4 USDH as input. How can we ensure the 4 USDH are valid? With the preamble, this is simple. The contract only has to check if the preamble is the SLP verify script. And that's it. The token is guaranteed to be valid by the preamble. But wait, there's more. We can make lots of crazy things with that. Can we build a decentralized stablecoin with that? Say we have a price oracle that continuously spits out prices. And we have a buy-sell contract that, depending on current prices, buys or sells tokens. This isn't how MakerDAO works, but it will be a good example. So let's say we're here. How can the bottom contract take the prices from the price oracle? We can't really just create a transaction that has both the oracle script and the buy-sell scripts. This would create a big mess in the preamble. How can we keep the preamble alive? So the oracle emits a message with the price and then just continues doing what it's doing. Then the buy-sell contract can take this message as input. How can the buy-sell contract ensure the message isn't fake? The same way as before, by putting a verify script on top into the preamble. It verifies the origin of the message. Then the buy-sell contract just checks if the input transaction has this verify script. This means we can do verifiable message passing between contracts. This allows a complex ecosystem of independent actors on the blockchain, which means we can make an actor for CDPs, an actor for governance, and so forth. They would require by passing messages between them. Does this mean that we could make a decentralized stablecoin on Bitcoin Cash? Like MakerDAO? Let's have a look how we could build MakerDAO on Bitcoin Cash. So there'd be one big main DAO that stores all prices and governance variables. And then an oracle would continuously update the prices of this DAO, just as we've seen before. So, and to change governance variables, a new vote can be initiated from the DAO. And this would be a new temporary contract. And owners of the governance tokens would do a vote with one big transaction with all the tokens as inputs and outputs. The resulting vote would then be fed into the DAO. And that would change the governance variables. So, and now onto the stablecoin part. A new collateralized debt position, CDP, can be created by anyone by simply calling a function on the DAO. Then collateral can be added to this CDP by the owner of the CDP. Then the stablecoin can be generated by taking debt from this CDP. And yeah, this is done. Yeah, and then this stablecoin can be sent and received just like any other token, like Tether or USDH, stuff like that. So to get the collateral from the CDP back, the debt first has to be repaid, obviously. And this is done by burning the stablecoin back into non-existence, where it came from, and additionally burning some of the governance token for the interest that has accrued. So, and finally, if the CDP becomes too risky, if the collateral becomes too little value, then the CDP will be force liquidated. This means the CDP gets turned into an auction contract that sells the collateral to the highest bidder. And yeah, that's it. Building a decentralized stablecoin like MakerDAO on Bitcoin Cash would be very complicated, but with the right tools and support, it shouldn't be much more difficult than building it on Ethereum. However, we need a couple of changes on the Bitcoin Cash transaction format for this to work. So, the main ones are MERKLIZED script trees, a new cache assembly, and a preamble. Yeah, additionally, we can also add fractional satoshis into the new transaction version, and a malleability fix. So, yeah, and we can also add stuff like Schnorr signature aggregation and input metadata such as block height to be added. So I made a small time estimation. How long would it take approximately to implement this? It requires a specification for all nodes, which will be done by lots of developers, a higher level language and tooling for developer productivity, and incremental and finally an incremental implementation into all nodes. So obviously this shouldn't be done all in one stroke, but this should be done in like tiny slices. So first add like just the general new transaction format and some very reduced set of cache scripts, and then later add stuff like preamble and things like that. So the sum would be around 250 days, and the total price around $300,000. Alright, that's it. let's make the best cash the world has ever seen, shall we?